In Section 6, you'll learn about the graphics device interface. GDI is the way your Windows programs will perform output on attached graphics devices. We'll take a look first at how you can access devices through GDI, then at how you can specify what the objects you draw should look like, take a look at how you can manipulate coordinate systems, and then we'll actually take a look at what it takes to draw pictures. With all that in mind, we'll be able to take a look at how you can save a drawing for later replay or reuse, perhaps on a different device. And finally, take a simple look at how GDI supports printing on hard copy devices. In the first module in this section about GDI, I'd like you to get familiar with some of the capabilities of GDI. We'll talk a little bit about what it is that you can expect GDI to perform, and then I'll have you go to the lab and, using a fairly simplistic application, explore the GDI using that SimTest application. Let's take a look now at the kinds of things that you can expect GDI to do for your program. First thing to notice is that GDI can draw on essentially any graphics device for which a device driver has been written. That is, you can use the GDI instruction set to draw on the system display, typically within your Windows. You can use GDI to draw on printers or plotters to create hard copy. Additionally, GDI supports your ability to save a sequence of stored GDI calls, we call those metafiles, as well as to store arrays of values. These are called raster images, and I'll return to that in just a moment. In addition to drawing on all those devices, GDI knows how to share those devices. When you have a number of programs running in Windows, they've all got to work together, and each of them will take a turn with the system display. And when you want to print a document from one copy of a word processor and print another document, say from a charting program, it's very important to you that all the pages of your first document should come out of the printer before any of the pages of your second document. GDI, therefore, has special mechanisms built in that allow it to share both the hard copy devices on your system, which largely amounts to serializing access to those devices, and sharing the system display, where windows may overlap and have arbitrarily strange shapes. In addition to the full range of capabilities in terms of devices on which GDI can draw, GDI has a full range of capabilities in terms of the kinds of graphics primitives that you can put onto those devices. It supports geometric primitives, things like circle, polygon, and so forth, which are defined by geometric coordinates. GDI can also handle such things as raster images. Another word for raster images would be cell arrays, or pel arrays, or pixel arrays, or rasters or frame buffers. All of these terms are equivalent. Now, the difference between them is that whereas a geometric object like a circle is defined by maybe a center and a radius, which are two sizes or lengths, if you will, or coordinate values, a raster is defined by an array of values at locations. Typically, those values are colors, perhaps, and the range of colors is specified by the number of different values each of the locations in the raster can take. GDI has a very rich set of raster functions with which you can manipulate such images. You can save them away, and later when you want to replay them, you can pour them, say using set bitmap bits, onto a display. Or you can move them around using the bit block transfer function. Bit blit is a phrase that comes to us from Xerox PARC. Additionally, GDI supports very near typographical text capabilities. Devices are increasingly able to produce really good-looking text, and GDI's interface to text allows you to access the text available in a device and find out a lot about its characteristics and to match the appearance on the display with the appearance on the hard copy device. That's what's called WYSIWYG, or what you see is what you get. And Windows has among the richest interfaces to text in the industry. I think you'll find there's a lot in it. Let me show you what you can do with the laboratory for GDI. The SimTest laboratory is one that we developed to test out GDI in the early phases of its development. It's a little rough around the edges as a program, and I think you'll find lots of ways to improve it, but it does a couple of things. First of all, it's got some of the world's largest menus. I mentioned them earlier when we talked about menus, multiple rows and columns. Those menus are there so that you can specify the way lines should be drawn, the way interiors should be filled, background color, foreground color, and so forth. Additionally, you can actually draw shapes with the SimTest. Using the shapes function, for example, when I click, click again, I can draw an ellipse, and so forth. When I want to pick something up, click, we'll move it around using the bit function. I think you'll find that the SimTest application is very helpful in exploring some of the capabilities of GDI. Don't spend a lot of time with it, but begin to become familiar. As we work through this section, I think you'll find that you go back to SimTest to work with and take a look at the code. I'll provide you the code as well for this. I'll see you when you've worked with SimTest for a little while, and then we'll talk about accessing GDI devices. Now that you're a little bit enticed about GDI, let's take a look at how you actually gain access to GDI devices. Turns out there are a number of ways to do that, and what I'll have you do in the laboratory is to alter one of the lab programs you've got, adding several different mechanisms of acquiring and releasing a DC, that is a device context, for the display, and I'll have you add a menu to the window so that the user can select which display they're going to see. In that way, you'll work on menus as well as GDI. The device context is key to gaining access to devices controlled by GDI. This DC is returned to you from the device access calls that you're going to learn to make in the exercise for this module. In order to use a DC, first of all you must obtain it, then you work with it for a while, and release it. It's kind of standard methodology in Windows. You do the same with any scarce resource. You acquire it, use it, release it, whether it be memory or file handle, and it's certainly true of access to a GDI device. Now, in order to keep things interesting, because that's a fairly simple scheme of obtaining, using, and releasing a device context, we provide at least 6 different ways to acquire a device context, largely differences in the kind of device on which you want to do some drawing. The device context is a piece of state in the system. It has a whole lot of information within it. It has information specific to the device. For example, if it's a hard copy device, what port is it attached to? It has information about the current attributes. If you draw a line, what color do you want that line to be? How wide do you want it to be? If you draw a filled figure, what interior fill pattern would you like to have? And that sort of thing. The device context also includes a coordinate transformation. Now, I personally think that's a very fancy phrase for what is effectively a renaming operation. We're not doing massive 3D rotations in hyperspace or anything. I mean, it's a very simple thing. And I'm going to try and demystify that for you in the module on coordinates. Finally, the device context also contains information about clipping. It's particularly important and relevant to the system display when your window, which has a rectangular client area, may have been trimmed by the occurrence of a menu or some other user interface item. Device contexts are the key to using devices in GDI. Now, let's take a look at the number of ways that you can actually access a device. The most general mechanism for accessing a device within GDI is the create DC mechanism. This basically gives you access to the entire device, regardless of any other competing requests for access to that device. When you create a DC, you provide the name of the driver file and a subtype. For example, we have one Epson driver that can operate on all of the Epson printers. So it needs to know whether it's talking to an FX80 or a GX or an FX150, etc. That's the subtype. Then you tell it the port, and there's a fourth parameter that nobody I know has actually used in any of their drivers to date, but which would ultimately allow you to transfer information into the device at startup time. Second example you've got there in your workbook shows you how you can allocate the entire display for drawing. Not typically what you want to do within Windows, but you can do it, and the Create DC mechanism allows you to. When you've done with a created DC, you delete that DC. So, these basic DC mechanisms of create and release allow you access to the entire device. But even more interesting, I think, for the interactive side of the programming we do, is gaining access to a Windows client area, or in some way for the window. There are a number of calls related to this that return to you a DC tailored for a specific window and its actual visible area. Get DC, well, you pass in the window. You say, I want a DC for this particular window, and you return to device context suitable for drawing on that window at its current location, its current size, and with all of the pop-ups and menus and all the other things accounted for in the clipping context part of the DC. The Get DC mechanism returns a DC suitable for drawing only on the client area pixels. If you want wider access, for example, you want to redraw your own caption bar or something else, you can use Get Window DC to get permission to draw on all of the pixels which belong to the window, including all the decorations around the client area. That is the caption bar, the menu, say, and the borders and so forth. When you've done with a gotten DC, that is whether you did Get DC or Get Window DC, you release that DC. And you have to tell Windows which window that DC was for. That way Windows can update and take care to ensure that it understands what parts of the DC, what parts of the picture are currently accurate and avoid telling you to redraw until things get out of date again. Again, you must release DCs that you get. Now those are pretty simple mechanisms. They don't provide you any additional information about the areas, for example, in the window that need to be updated. A lot of times it's very important to you to know that. Particularly those of you coming from the Macintosh universe will wonder, where is the update region? Well, here it is. We provide another mechanism for acquiring a DC for a window called Begin Paint and End Paint. Begin Paint returns a handle to a DC, a device context that's suitable for drawing on the client area only of the window. In fact, that DC is further restricted to only allow you to draw on the areas of your window that need to be updated. For example, if a message box has obscured or overwritten some of the pixels on your client area, the Begin Paint mechanism will make sure that you just update those pixels. Begin Paint then is a macro. It returns to you a filled-in LP paint structure. The paint structure is a data structure which has information about the area of the window that needs to be updated. So when you want that information, for example, if the bulk of your client area is all white space, then you may not need to regenerate information. Just because the system told you to paint yourself, you may know that there wasn't any important information that got damaged. Needs to be repaired. So the Begin Paint mechanism is a help to you. It performs other services, for example, telling Windows that you've drawn things and made them up to date, and so forth. Now those are 4 mechanisms for gaining access to DCs. Create DC gets you a DC for the whole device. Get DC and Get Window DC gain access to a window for you, but they don't provide any additional information about what parts of the window need to be updated. Begin Paint is a more complicated mechanism that provides you the additional information you need to make incremental updates of your client area instead of wholesale repainting the whole thing every time you're asked to redraw parts of it. The other 2 mechanisms that I want to discuss are related to either recording a sequence of GDI calls for later replay or managing off-screen bitmaps. Our metafile mechanism allows you, after you have created a metafile, to make a sequence of GDI calls using the DC for that metafile. When you close the metafile, you get back a handle, which you can then use in the play metafile command. Or you can retrieve it and put it in RAM, or you can write it out to disk. Metafiles are fairly flexible, and they can be stored long term. They need to be used with a little care. You have to be watchful of the way you use coordinates within a metafile. But they can be very useful for replaying drawings before they reach the device coordinate level. Finally, in order to save bitmaps or move them between a file, for example, or a resource bitmap that you may put in your application, and onto a display or a printer, you need to understand the mechanism of working with memory devices. A memory device is suitable only for devices which have underlying raster technology. That is, things like printers or displays that can illuminate dots with colors or intensities. There are two things you need to do in order to create them. First of all, you must have a DC for the device that you want an off-screen bitmap similar to. So the first thing you do is to create a DC for the device that you want to have an image of off-screen, be it a printer or a plotter. You then create a compatible DC using the GDI call for that purpose, and handing in the DC for the original device. What we will return to you is a handle to a memory device. Now this is kind of a strange device. You can draw on it all you want. Nobody's ever going to see it. But it's a great place to marshal your drawing off stage, if you will. And then you can just move it right up stage where people can see it. It's also the only way that you can move raster images onto hard copy devices. You must use a compatible bitmap within memory DCs, and so you'll also learn how to allocate bitmaps. In order to keep things fairly simple, in the case of this laboratory of accessing GDI devices, I'm not going to have you do any printing, I'm not going to have you access any off-screen memory devices or anything like that. I need to show you what this application looks like because you're going to find its behavior a little bit strange. The first way that you can access the device is by painting on the client area. Now, that's the routine way that a typical Windows program works, and if I change the size, this program is going to redraw itself. I think you've seen this before already. But what I've added to it is another kind of DC, the window DC. Now, when I allocate a DC for the window, that gives me permission to draw on all the pixels within the boundaries of this window. And since I'm not adjusting my drawing at all, it's going to be offset, and it's going to be relative to the upper left-hand corner of the window. That is right up to this upper left-hand corner instead of this one here. So when I select the window DC and do a get window DC mechanism on it, I get a pretty strange drawing. It draws all over the caption bar. Menu's still there. I can work with that. If I go back to the client area, I get a picture that's just as it was before. Finally, I'm going to also have you access the entire display, just to prove to you that you can do it. And again, you're not going to adjust your drawing, and so all of a sudden the rectangle that you're drawing, instead of being relative to your client area's upper left-hand corner, or relative to your Windows upper left-hand corner, now all of a sudden the drawing that you do is going to be relative to the display's upper left-hand corner. That destroys some pixels that aren't really yours, but it will allow you to gain an understanding of the way in which you need to invalidate, validate, and erase background, and so forth and so on, to work with your windows. You can always restore things by zooming and then coming back when the display is client area. So I want you to go in and work with the code that we've given you, and then when you're satisfied that you understand these device access mechanisms, come on back and let's take a look at how can we change these lines, the colors of them, and do some more fancy looking stuff. Well, now that you're convinced that I built you a very strange laboratory exercise, let's go on and do a little bit that may seem less strange. In particular, I'd like you to learn now about the features and the aspects of GDI which allow you to control the appearance of things that you draw. We call them objects, and I'll refer to that in the lecture and explain that. But in the laboratory, I'm going to have you add a bunch of pens and brushes to your Windows program, and then also allow the user to select them. Attributes in GDI are what control the appearance of the objects that you draw. For example, the pen attribute specifies how lines should appear when GDI draws lines. The brush attribute specifies how interiors should be filled when you draw a filled shape, say a circle, some sort of solid figure. GDI also supports what I call blind interchange. Now, it's very important that you should be able to specify some attributes and then have the user hook up to a device that can't support them and still have your program function in some way or another. So you specify the attributes you want, and GDI and the device work together to achieve the closest thing to that appearance. Now, some attributes have been grouped within GDI. If you think about lines, after all, lines can have width, they can be interrupted, that is styled, dotted or dashed or what have you. Fill patterns may not be patterns at all, but may just be hatched lines drawn at angles. All of these things we have built into what we call bundled attributes, a la GKS. Those of you familiar with the standard graphics language GKS or with the evolving ANSI CGI will be familiar with the notion of bundled attributes. And GDI is a bundled attribute system. When you want to specify how a line looks, you build a pen. The pen has a width, a color, and a style. When you want to specify how interiors should be filled, you create a solid brush for a color, or you create a hatched brush with the hatched lines taking on the color that you specify, or you create a pattern brush. Later on, when you select them, they become the way in which GDI does its work. Fonts are an area I referred to just briefly earlier. In GDI, you have a very rich set of requests that you can make for a font. You can ask for 18-point Helvetica, rotated 14 degrees, bold, and in italic. GDI will then match, or do the best it can to match your request for a font with the font best suited that's actually available on the device. There are other attributes that are individual attributes. For example, foreground color, which is used as the color in which text is drawn, is a singly specified attribute. There's no way to bundle it together with anything. Background color is another such attribute. It's singly specified and is used when the background mode is opaque. The background color is used for the spaces between hatched lines in hatched brushes, and for the spaces between interruptions in styled lines, for example, and so forth. ROP2 is our name for the Boolean operation we'll perform when we draw a line. XOR is the one that you'll be most concerned with so that you can remove a line that you previously added. There are other attributes. And as you get to know GDI, you'll study them and increase your facility with the use of these attributes. Now, when it comes to using a GDI attribute, and here's a place where I think I want you to make some notes in your workbook, because you'll use these notes in order to help develop your laboratory. First of all, you create the object. At the time you create it, GDI will take a copy of the specification for the object and put it into its own data segment, its own data area, returning to you a handle. Now that handle is not the same as a handle to memory or a handle to window. It's a special GDI handle. But with that handle, you can refer to the object. If you want to use the object, for example, to draw on screen, you select it into the DC for the screen. Later on, if you want to use the same attribute object to draw on a printer, you'll select it into the printer's DC. Well, then you're ready to draw, now that you've specified how the attribute should be and selected the attribute in. Before you throw it away, it's important to put back the original object. Every time you select a new object, you get back the original one. And you'll see in the exercises that you save that away briefly. Then you reselect the original, getting back your new one, you delete your new one, and you're ready to go. That's the way you work with attributes. And now you're ready to go. Let me show you what the lab's going to look like before you go off to the lab. Okay, with the information you've got, you're now ready to go off and do a lab using attributes. The appearance of your window is going to start to take on a little bit more interest. Here I've built a system in which I can change the pen that's used. The red pen here is pretty narrow. It's also dotted, not real obvious. And I can change the brush that's used for the interior color. I've kept the ability to redraw on various different locations, and basically I'm just building this application through the entire GDI. Go and work with some attributes, and then come on back and we'll talk about coordinate systems. Now that you've worked some with attributes, let's take a look at coordinate systems. GDI provides a number of different coordinate systems so that you can control the way in which GDI interprets and uses the numbers that you use to draw circles, lines, polygons, and so forth. We'll talk about them, and then you'll go into the laboratory, add another menu to your application to allow your user to select from a number of different coordinate systems. You will then redraw your output using that coordinate system. The goal here is that what you're building up through this section is a GDI playground. It's a place for you to go and learn about a lot of these capabilities. The use of coordinates in GDI is really involved with your specifying numbers and the system's then sending numbers on to the device that you're talking to. GDI's coordinates control the locations of things. They're pairs of 16-bit integers, what some people have in the past called pseudo-coordinates, because they're fairly limited in their bandwidth. There are not a lot of values that you can take on with only 16 bits. It is useful, however, because we can pack an entire point, an XY location, into a 32-bit double word. The first thing that you must decide in using GDI is to specify to GDI, or to make a decision as to what the coordinates you use when you talk about drawing objects mean. You need to decide whether these coordinates mean device addressable units, that is, go to some location on the device, and the coordinates you're using are really the names for those locations already, or whether what you're talking about is physical dimensions. Perhaps you stored coordinates in some English or metric coordinate system. You can tell GDI that, and GDI will then interpret them appropriately, make the arrangements on the device necessary to make those coordinates happen for you. You may specify that, well, you don't really care so much about the resulting physical size of the picture, but that you do care that its aspect ratio remain the same. That is, you want squares to remain squares. Perhaps you want circles to remain circular, not turn into ellipses just because of the user's manipulation, say, of the size of a window. Those are called square scalable coordinates. Those of you with mathematical inclinations will know them as isotropic transforms. You may be thinking in terms of coordinates that you don't care about the shape of them ultimately. These we call non-square scaled coordinates, otherwise known mathematically as an anisotropic transform. And it provides what I like to think of as the rubber sheet method for covering the entire area with your picture. So the first thing you need to do is to choose the coordinate type. You need to choose and specify to GDI what information it is that you want to preserve. In particular, you might choose device coordinates if you're already storing 3D coordinates and you're already doing mathematical transformations on them. Best thing to do in that case is to check out the device, pull the device coordinate system up to your level and do a single transformation. That way you avoid heating up the numeric processor twice in order to achieve coordinate resolution. You can avoid multiple transforms by using physical coordinates, and you can also avoid problems with integer round-off. You never quite know where a number is going to fall in a device coordinate if you're not paying attention. Choose physical coordinates if you really care about the size of the output. If what you're building is output that has to fit on a 3x5 card or onto an envelope or something, because you're going to mail it to somebody, you may care about the exact physical size. Choose square scale coordinates if the shape of the drawing is important to you, but you want to allow the user to zoom in or zoom out. Finally, choose non-square scaled coordinates if you want to cover the entire area that's available. It actually falls out of the set of transforms, and it's kind of interesting. It's what we've been doing in Simple, in fact, all along. In order to set a coordinate type in a DC, you make a call set map mode. We provide parametric names defined in Windows.h for all of these coordinate types. We call device coordinates text. That's for historical reasons. Comes to us from the world of the Macintosh, where in fact the Macintosh screen has 72 scan lines per inch, and it's very, very close to being a printer point high per scan line. Low metric, high metric, low English, and high English are the physical dimensionalities based in metric and English terms. We also have one called TWIPs, TWIPs, 20ths of a printer point. They aren't quite, because a printer point is actually 72 point something or other of an inch. But think of a TWIP as 1/1440th of an inch, and you won't go far wrong. Finally, we provide isotropic for square-scaled coordinates and anisotropic for the non-square scale coordinates. Now, once you've specified what the numbers you send to GDI mean, they may mean portions of inch, or they may mean stretchable coordinates, or whatever they mean. You must also specify to GDI what parts of the coordinate range are you interested in. Typically, that's known as the window to viewport transformation in the standard graphics terminology. We've reused the word window here. I apologize for that. But it's very important that you understand that that window is different than the window on your screen or the windows you create with Windows. In any case, you've got to alert GDIs to the coordinate values you care about, the ones that are of interest to you. You do that by specifying an origin in the window space, which is in the coordinate system that you've set using set map mode, and an origin on the device. The origin on the device, the viewport origin, is in fact in device coordinates always. Our viewport system, for those of you who know graphics languages, is not a normalized device coordinate system for viewports, but rather a device addressable unit notion for viewports. The window origin on your coordinate space is glued, if you will, right on top of the viewport origin, and you can move them around relative to one another. Similarly, your square-scaled coordinate types must specify extents in order to help Windows figure out where you want to draw. Maybe all of your drawing lives between 0, 0, 100, 100. Maybe all of your drawing lives between 8,000, 8,000, 9,000, 9,500. And you've got to locate for GDI the portion of the coordinate space that you actually want to see. Got some pictures in your workbook showing you what happens if you use text on devices with different aspect ratios. If you use physical sizing on a device with different size, notice that you get clipped if the image isn't big enough. Isotropy preserves the shape of your drawing, regardless of maybe the shape that you're drawing into, but it does throw away some pixel area, and people have paid a lot of money for that. So that leads to the rubber sheet transform, the anisotropic transform, which covers the entire available area. When you go to laboratory, you're going to work with coordinate systems. Let me show you what that's like in a minute. Okay, you're ready for a lab on using GDI coordinate systems. What you'll do, bet you can guess already, you're going to add another pull-down menu, and you're going to allow the user of your program to decide whether the drawing you're doing is in pixels, in inches, choose metric if you feel that preferable, is a square scale drawing, or whether it's anisotropic. Now notice that anisotropic is what we've been using all this time. If I were to draw isotropically, I drew a rectangle in a square space, so I'm going to get a square. This thing is, some rectilinear shapes are in fact squares. If I draw in inches, I'm going to get something that, in fact, if I walk up here with a ruler, take a look at my display. It's probably optimized for about a 12-inch screen, and I bet that thing is in inches. If I do it in pixels, then it's going to be 100 pixels and 100 pixels. So users will be able to mix and match the actual type of the way in which they're using the coordinate system once you've done this exercise. Now that you've worked with specifying the appearance of things and locating things, let's talk about what you can actually do. In this module, we'll review the geometric functions that GDI provides and the raster capabilities of GDI. In the laboratory, you'll actually use some more geometric functions and the raster functions to extend your laboratory application. With GDI, you can draw various different kinds of shapes. In particular, you can draw geometric shapes which may be filled or not filled, mostly based on whether they are closed or not closed. That is, it's easy to fill closed objects, and it's tougher to fill an object that doesn't quite achieve closure. All of these are specified by a function name. And in general, there are two kinds of geometrically defined objects. There are those which take the name of the function and then a list of points and a point count, such as polyline and polygon. And there's another set of them that take the name of the function and then the upper left-hand corner or the lower left-hand corner or the bounding box for the primitive. Circle, for example, is defined by a bounding box. Ellipse, rectangle, all of those are defined by the bounding box. I don't have a lot more to say about the geometric functions. I think that the best way to learn to use them is to actually work with them. In the lab for this geometric function module, I want you to go in and add to your drawing a number of additional kinds of constructs. What I've done here, for example, is I added an ellipse and a little polygon. Then you can go back and maybe change the fill style or the attribute of the brush that you used at the time you draw the ellipse and the time you draw the polygon, or change the pen. Work with these attributes and get familiar with the way in which you can add geometric shapes to your Windows application. I'll see you when you're back, and then we have to discuss raster primitives. They're a little bit tougher. Okay, now your pictures are starting to actually look a little bit like something. Let's talk some about how GDI promotes and provides raster capabilities for you. First of all, let me reiterate that rasters have many, many names. Some people call them bitmaps. Otherwise, they might be known as pixel arrays, or pel arrays, or cell arrays. Frame buffers are a way that displays make rasters visible to people. But all of these are names for an entity which is an array of values at locations, typically rectangular. And the values are often interpreted as colors or intensities of one color, say, for grayscale kinds of devices. The result of this organization is that there are two ways to organize rasters in memory. You can either organize them so that all the bits that make up one value in one location in the array are together. As shown in your workbook here, that's called a packed raster representation. The other representation is a representation typically called planar, where what you have instead is all the 0 bits for all the values, and then you have all the 1 bits, and then you have all the 2 bits. Each of these organizations is about equally common. There are certain advantages electrically and manipulatively for both, and we provide within Windows, GDI, the ability to work with devices whose underlying architecture is either planar or packed. Once you have an array of values, consider that the locations are spread in space, and the depth specifies how many colors can occur at each location. And as soon as I've got a two-dimensional picture and a third dimension, I have the opportunities to resample these rasters. For example, if I have a small raster that I took, it was originally 1/2 inch by 1/2 inch, and I want to blow it up to be 3 inches by 3 inches, I need to stretch it. I need to duplicate some of the values. Similarly, if I scan in a very large picture, say at some very high resolution, I want to show it on a display, I may have to shrink it down. GDI supports sampling in space through the stretch split operator. In fact, we support 3 different ways to sample. In particular, if you're compressing an image, there tends to be some things that happen. If you have, for example, a very geometrical image with a couple of circles in it, if you OR all the bits together, you tend to get a picture that remains stable. But if you require that all the pixels that are being compressed be on before you turn on the result pixel, that's the AND mode, what happens is in a geometric picture, quickly you get holes in the circles and so forth. On the other hand, if you start with a halftone image, where you have lots of values, lots of noise, if you use the OR mode, so that if any pixel is on, then when you squeeze it down into a target pixel, that target pixel is on. You tend, as you shrink the halftone, to turn it into black. Now, there's a universe of image operators. We're talking now really about image operations. It's a fruitful subject for research. I don't regard GDI as providing much help in this regard, but we do provide 3 modes. So when you do a stretch split, you get to specify whether it's an AND, an OR, or a drop. You can study those and work with them in the SimTest application. Finally, you can also sample in depth. Now, the most important depths are 1 bit per pixel, on or off. Typically, that's the way we store text bitmaps for use on raster displays. If I want text to take on a color so that the foreground text is a color and the background is pushed to the background color, then I need to sample in color. GDI supports conversion from 1 bit of color per pixel into whatever the native color mode of the device is. With these techniques and technologies, you can take your raster images from a scanner, say, and put them in living color into your documents, show them on the display, and then print them out on a printer. There's some mechanics that you need to understand. And so there's a laboratory related to using rasters. With that little bit of background about rasters, I'd like you to go off and work with raster functions. In this laboratory, one of the things to do is to simply allocate an off-screen bitmap as the place in which you perform your drawing. What I've done here is to simply add a 4th kind of display. And when I select bitmap as display, what I do is I create an off-screen bitmap, I draw there, and I move it onto the surface of the actual client area here. This application then has been expanded in terms of the number of drawings it can make. So, go on to the lab, work with rasters, work with SimTest too, practicing with stretch split as well. And then come on back and let's talk about saving your work. Now that you've worked with GDI some and have prepared drawings and so forth, it's time to spend a little bit of time looking at how you might save a drawing. In this module, we'll talk about metafiles and bitmaps, and then I'll have you go off to the laboratory and actually create and use a metafile and use a memory DC for drawing, saving and restoring the bits in both the bitmap and the metafile. When you'd like to save a drawing, you're going to make a choice between using a metafile or using a bitmap to save that drawing. Both of these are pseudo devices. Both of them are available to you through the device access mechanisms of Create Metafile DC and create compatible DC. The advantages and disadvantages of both include the following. Metafiles are literally sequences of GDI calls. You can store in a metafile attribute selection, attribute creation, coordinate transformations, and so forth. When you've closed a metafile, what you have is an object that you can carry around. You can put it into a file, you can reread it later on. When you've got it in storage, you can play that metafile through any DC. Now, disadvantages of a metafile include the fact that if you have coordinate specifications, in particular viewport specifications, within the metafile itself, they replace the viewport as it currently exists. It is therefore, in general, a bad practice to work much with viewport setting within a metafile. It's okay to set the window, and it's also important to remember how the transforms were set when you created a metafile. The advantages of a metafile over the bitmap representation are that when you eventually draw them onto a device, the line will get drawn out in exactly the resolution of the device. We will not have to make pixel sampling kinds of activities. So metafiles are good for replaying particularly line-type drawings. Bitmaps, on the other hand, are rectangular arrays of values, color or intensity values. They can be placed on any device in general. It's hard on a plotter if you wanted to do bitblit, but you can ask at least. It's hard on the pens and the solenoids and so forth. But raster images can be saved and manipulated. Now, one thing you might do, for example, is to create a drawing in an off-screen bitmap area, get all the bits from that, save those bits away. Later on, create another off-screen bitmap and pour the bits back on with set bitmap bits. Those are the basics for the way in which you can create data structures, a metafile or a bitmap that you can save and maneuver in the system. Let's take a look at what you can do in the lab. The first of the pair of labs for this module will guide you through the addition of a metafile, its creation, its use, and its reuse. I'm not going to show you the application because it doesn't look any different. You're just going to replay the same picture that you've been creating. But you'll do it through the mechanism of a metafile. Welcome back. The other of the pair of labs in these labs will guide you through the use of a bitmap. Building an image on a bitmap and then getting the image into your own data area where you could transfer it to a file as a data structure and restoring it as the bitmap. Again, the picture doesn't change, so I've not included an example of your application, but the lab will guide you through some of the initial and earliest and easiest ways to use a bitmap. The other thing you may want to do, in addition to saving your drawing, is to actually create some hard copy of it. In this module, we'll take a look at the way GDI controls printers, and then you'll go back to your application and actually use the GDI printing functions to print out your drawing. GDI allows you to gain access to lots and lots of different kinds of devices. Among them are the hard copy devices, printers and plotters and the like. Because of the peculiar characteristics of these particular devices and the fact that displays don't share these characteristics, we have captured all of the special printing functions within GDI in the escape calls. The GDI escape call is, if you will, a standard way to be non-standard. And in fact, one of the escapes allows you to pour data at a device directly through the GDI interface. But among the escape calls that are very important to you in your creation of a document are those related to document control on a device which creates hard copy. In particular, escape functions such as start doc, new frame, and end doc are the escape functions that you will use in telling a printer to open a new document, begin a new page, and eventually to close a document and tell it to begin printing. There's some other aspects of the use of a printer related to more fancy finesse, for example, allowing a user to halt the spooling of a document to be printed as you're doing it page by page. In general, though, I want you to understand that the escape function in GDI is where we can expand GDI without doing damage to the interface itself. And that the escape functions in GDI are where you will find things that are fairly device-specific and fairly technology-specific. You're ready now to go off into a lab and actually print a simple document. In fact, what I want you to do is to simply print the image that you've been drawing in your client area. I want you to figure out what your printer is and use it, and you're going to code that right in. Later on, we'll come back and look at win.ini, but for now, go and print yourself a document and see how easy it is to shift from the display to the printer.